All right, in this section we're going to learn how to find the derivatives of the other trig functions. In the last section we worked with these two formulas, the derivative with respect to x of sine u, that's cosine u, times du dx, and then the derivative with respect to x of cosine u is negative sine u times du dx. There are, of course, four other trig functions: tangent, cotangent, secant, and cosecant. The first formula here, the derivative of tangent, that's the one we derived together at the last example in the last section. And we did that just by seeing that tangent was sine over cosine, and so we could use the quotient rule to find that derivative. And I bring that up because all of these formulas, all four of these, you could find in a similar way. Cotangent is cosine over sine, and if you use the quotient rule, you'll figure out that the derivative of cotan should be negative cosecant squared. Secant is 1 over cosine, so you can write that as 1 over cosine, or cosine x to the negative 1, and use the power rule. Similarly for cosecant, cosecant is 1 over sine. And you can derive those formulas. And I bring this up just because once you use these enough, you'll learn to memorize them. You'll come to just know those formulas. And flashcards also help. But if you ever forget it and need to know it, you can derive it as long as we know these two formulas at the top. So in this section, we're going to get some practice using these formulas. Let's begin. We want to find the derivative of y equals 2 tan of 8x. So let's just start. This is a basic function in that there's no product involved. It's not stuff to a power. It's just a tangent function with a coefficient. So I bring down the coefficient. The derivative of tan of 8x, the derivative of tangent is secant squared. And then the chain rule says I have to multiply by the derivative of 8x, so I multiply by 8, and we get 16 secant squared 8x. All right, let's try another one. We want to find the derivative of this function, y equals 3 times secant squared 4x. 4x is the argument, when x is 0.2. Now, one important note, this, x is part of the argument of this function. And so we should just be aware that if x is 0.2, that this means that it's radians. Our calculators will need to be in radian mode. In general, when you're working with trig functions, your arguments are in radians unless they specify otherwise. So our function is 3 times secant squared 4x. I'm going to rewrite this because if we're squaring, the secant squared means we're squaring the whole secant function. So I'm going to rewrite this as 3 times, and then I have secant 4x all squared. This is a power rule derivative. And I'm going to have to take the derivative of secant, but that'll be a part of the chain rule. So applying the power rule, we bring that 2 down, multiply it by the 3, oops, that's already there, so we have 6 times, and then we have secant 4x to the first power. And then the chain rule says we have to multiply by the derivative of what's inside, the derivative of secant 4x. That's the next layer down. So the derivative of secant is, I'm going to scroll back up here, the derivative of secant is secant tan. So this will be secant 4x tan 4x times, and now we're going to multiply by the derivative of what was inside secant, so times 4. Again, we have a function inside a function inside a function. You could see why we really call it a chain rule. There are multiple links here. All right, so I've got a 4x function stuffed inside a secant function, stuffed inside a squared function. Simplifying this, we've got a coefficient of 24, and then secant times secant is secant squared 4x times tan 4x. So there is dy dx. Now, it says that we want to find the derivative when x is 0.2. So let's finish this up, and we'll plug in 0.2. I'm going to rewrite this first a little bit because I don't have a secant button on the calculator. So I'm going to write this as 24 times tangent of 4 times 0.2 is 0.8 over cosine squared, right? Secant squared. Secant's 1 over cosine, so if I have a secant squared factor, that's a cosine squared in the bottom. And let's plug this in the calculator. My calculator is in degree mode right now, so I'm going to change that to radians. 24 tangent 0.8 divided by cosine 0.8 squared. I'm squaring the whole cosine function, and that's 50.91. So increasing quite steep. Alright, let's try another one. Our function here is y equals t times cosecant cubed of 2t. Again, the 2t is the argument inside the cosecant function, and we are cubing the cosecant function. So I'm going to rewrite this as t times cosecant 2t all cubed. So we can see that we have like stuff raised to a power. There's part of this is going to involve a power rule, but overall the structure of this function is that it's a product. I'm multiplying two things. They both have our variable t in there, so we've got to set ourselves up for the product rule. So our f function is t, which means f prime is just 1. And our g function is cosecant of 2t all cubed. So that's a power rule derivative. So we'll bring the 3 down. And I have cosecant of 2t squared times, and the derivative of cosecant, if you go back to that first page of this section, that derivative is negative cosecant 2t cotan 2t. And then one more layer to the chain rule here, multiplied by the derivative inside the cosecant function, so we're going to multiply it by 2. Cleaning this up a little bit, we get a negative 6 times, and let's see, I've got a cosecant squared times cosecant, so we've got cosecant cubed 2t times cotan of 2t. So dy dt, this is g times f prime plus f times g prime. And let's see, g times f prime, that's going to be cosecant cubed of 2t times 1. Plus f times g prime. That's t times that function we found there for g prime times negative 6 cosecant cubed 2t cotan of 2t. I'm going to clean this up just a little bit, and then we'll do make maybe another move to simplify. So I've got cosecant cubed 2t at first, for our first term, and then minus 6t cosecant cubed 2t cotan 2t. And then I think we could do one more thing to simplify. There's a common factor of cosecant cubed. So let's factor that out. So inside now we've got 1 minus 6t cotan of 2t. There's our derivative. Okay, let's do another one now. We're going to find the derivative of this function, y equals tan 2x plus secant 2x all cubed. So this one I think is more like pretty clearly recognizable as a stuff to a power, right? That's definitely a power rule derivative. That's its overall structure. That's the outer layer of this function. So that governs how I start taking the derivative. And let's sort of just begin that process. dy dx. Applying the power rule, I'm going to bring the 3 down. Then I have this stuff as is. Tan 2x plus secant 2x squared times. Now we're going to apply the chain rule. So we're going to multiply by the derivative of what's inside that, the cubing function. So the derivative of tan 2x plus secant 2x. There's 2 terms to that expression, which means I'm going to just take the derivative term by term, and I have to make sure that I'm multiplying by the entire derivative, so I'm going to open up parentheses. The derivative of tan 2x, that is secant squared 2x times 2, because that has its own, chain rule going on, and then plus the derivative of secant 2x, that would be secant 2x tan 2x times 2 again, because that has its own chain rule going on. And then that sort of finishes out our first kind of phase of this problem. We have taken the derivative. The expression we have here is in fact equal to the derivative. It's just not simplified, and we can't stop here. So to simplify, I'm going to focus on this stuff at the end, what we wrote out for the chain rule. We have some common factors. We have a common factor of 2, and we have a common factor of secant 2x, right? It's important that it's not just secant, but it's secant of the same argument. That's what makes it a common factor. So I'm going to take that out of that set of parentheses. We have 2 secant 2x. And then inside, to bring me up to the secant squared, I need to pick up a factor of secant plus, and for the second term, I took out the 2 and the secant, so I'm left with the tan 2x. All right, we've got a little bit more that we can do. I'm going to throw this secant, in fact also the factor of 2, out in front. So we have a coefficient of 6 and then a factor of secant 2x times, and now if you look at this, tan 2x plus secant 2x, that's equal to secant 2x plus tan 2x. It doesn't matter what order you add two things together. Those are the same factor, which means I've got that stuff squared here, and I'm multiplying by the same base to the first power. I'm just going to add those exponents. So I have tan 2x plus secant 2x cubed. And that's about as simple as this one will get. Alright, so we've got some practice doing these derivatives of the other trig functions. Let's make it just a little bit more interesting. And we will do an implicit problem. So here we have an equation that defines an implicit relation between x and y, and we want to find dy dx. So I've got cotan of 2x, so there's the argument inside cotan, minus 3 times cosecant of x times y equals y squared. So overall, in this equation, right, I've got 2 terms. on the left side. I've got that cotan term, you know, we can take that derivative, and then we're subtracting this cosecant term. We know how to take the derivative of cosecant. We have to be careful about the chain rule here. So let's actually just start this. Let's take the derivative on both sides. On the left side, we have our first term is cotan 2x. So the derivative of cotan is minus cosecant squared 2x, so the argument stays the same. We apply the chain rule that says multiply by 2. Then we have this factor of minus 3. We're moving on to the next term. So I'm going to bring down the factor of 3, so I'm subtracting 3 times, and now I'm going to just focus on this part, cosecant of xy. The derivative of cosecant is minus cosecant cotan. We just keep the argument the same. Times, now we have to multiply by the derivative of the stuff inside, and that is a product. So the product rule now is coming up when we are applying the chain rule, right? So our f function is x, that means f prime is 1. Our g function is y, and that means g prime is, let's see, well that would just be dy dx. And we're going to use our product rule, which is g f prime plus f g prime. G f prime is y times 1, so just y, plus f g prime, that's x dy dx. Alright, so now we have taken the derivative of that second term. On the other side of the equation we have y squared. When we take that derivative we get 2y dy dx. The first phase of this problem is done. We have differentiated both sides with respect to x. I'm going to clean it up a little bit before we start the process to kind of solve for dy dx. So let's see, we have a minus 2 cosecant squared 2x, and then this is a plus 3 cosecant xy cotan xy times y plus x dy dx equals 2y dy dx. Alright, so we've cleaned this up. Now our goal now, right, we want to solve for dy dx. And the thing we need to focus on first is that one of our dy dx's is trapped inside this set of parentheses. And so we're going to approach that, we're going to fix that problem the way we've done it in the past, and that is we're going to distribute. We're going to take this factor out front, even though it looks big, you know, it is a big factor, but like whatever, it's still just a factor. I'm going to send that through. I'm going to distribute it to each of the 2 terms in the parentheses. So when I distribute it to the y, we'll have a 3y cosecant xy cotan xy plus, distributing it to x dy dx, we have 3x dy dx cosecant xy cotan xy equals 2y dy dx. Alright, now the dy dx is no longer trapped inside parentheses, and so we can get all of our dy dx's on one side. I'm going to subtract 3x dy dx cosecant cotan from both sides. So we've got minus 2 cosecant squared 2x plus 3y cosecant xy cotan xy. That's what we've got on the left. On the right, we've got 2i dy dx minus 3x dy dx cosecant xy cotan xy. Now we're getting close. You probably know what's coming next. We have all of our dy dx's on the right. They're by themselves all on the right. So let's factor out the dy dx. So we have dy dx, and in the parentheses 2i minus 3x cosecant xy cotan xy. And now, the very last step is we just divide both sides by the stuff in those parentheses. And when we do that, we get our final result is that dy dx is, see, we got this stuff on the left side, minus 2 cosecant squared 2x plus 3y cosecant xy cotan xy all over the stuff in this parentheses 2i minus 3x cosecant xy cotan xy. And there we go. So again, the process for these implicit problems is basically the same. It can get a little messy algebraically. We've got to be really careful with our algebra. But if we've taken the derivative, if we've done this first step correctly in differentiating both sides with respect to x, and then are careful with our algebra, even though we get a result that looks a little ugly, the process is basically the same as we've experienced it before.